Hi, welcome to this Physionic long-form video. I've been debating what exactly to call these. I keep calling them long-form videos, which technically that's true, but I've been thinking to myself some other synonyms that I can use for these more detailed breakdowns of the studies that we've been going over the many months. The extended versions, expanded versions, I don't know. If you have any ideas, please comment. I need something that's kind of a catch-all term that I won't feel tempted to change years from now. But that said, this is going to be a detailed breakdown of trying to answer the question of does caffeine improve endurance performance? So endurance performance being defined as running, cycling, rowing, really anything that's going to be a long duration type of exercise, or if you're going to be doing some sort of competition, like if you're going to be doing like a marathon, for example, then or a triathlon, that would all fall into that category. To answer that question, we're going to be looking at 3 different studies. Usually I limit it to one study, but these studies are really simplistic. They only have a few pieces of data, and they were done roughly the same way with some slight variations. So it'll be easy to lump those together into one video. So I'm going to be giving you a ton of information in this video, actually, if I can look at my notes real quick. So this is what we're going to be covering. One, the main question of does caffeine improve endurance performance? If it does, how much does it improve endurance performance? How much caffeine actually translates to better performance? So what's the amount that you should be consuming if it turns out to be beneficial? Does everyone experience that same benefit? And we're also going to be discussing the mechanisms for, or at least some of the proposed mechanisms for how caffeine might have this potentially beneficial effect. And then at the end, I'm going to go ahead and tell you that I'm going to tease you into the next video that's going to be discussing an exception to this rule that actually applies to a pretty sizable amount of the population. So the results that we're going to be covering in this video, there's going to be an exception to that that I will then introduce in the next video. But we're covering a lot in this episode, so be sure to stick around. If you're not familiar with who I am, my name is Nicholas Verhoeven. I'm a PhD candidate in molecular medicine, and well, that's about all you need to know. I'm doing this in terms of just breaking down research. I've been doing it for many years. And this is going to be a fun one. I think a little more lighthearted than some of the other ones that I've done, on cell metabolism and fatty acid oxidation and all kinds of different other aspects, sirtuins, and I mean the list goes on. So if you're interested, then stick around on Physionic because I'll be covering a lot more. But with that introduction out of the way, let's go ahead and jump into this. So, like I said, the overarching question that we're going to be answering is, does caffeine improve endurance performance? But we're going to be covering a lot of the other aspects as well. So this information is going to be coming from 3 different studies, as I mentioned, and they use a relatively similar study design that I'll go over in just a slide or two. But I broke these down. Usually I have a number that I've attributed to each study, but those are not within a particular series. They're just a continuation of all the studies that we at Physionic, that I have read and broken down for you. So then you can just look up the study number. However, in this circumstance, I'm going to be using letters. So as I go through the data, I'll be able to reference the letter so that you can just go back and look at the study title. I'll have the studies linked for you as well, so you can go over them for yourself. So obviously A, B, and C for these 3 studies, all of them investigating either cycling or running. But again, if you were to ask me, does this apply to something like swimming? Does this apply to something like rowing? I would say yes, probably. Okay, so the study design. This is sort of convoluted, but also extremely simple. So let me break that down for you. Like I said, the three studies were broken down between running and cycling, and two of them were on running and one of them was on cycling. And they used a similar procedure for the administration of caffeine. So caffeine was consumed at either 3 milligrams, which is the quote unquote low dose, or at 6 milligrams, which was considered the higher dose. Now, one study did also look at 5 milligrams, but I'm going to be focusing on the two extremes, 3 and 6 milligrams. So for some of them, you have two conditions of caffeine, and then you have the third condition, which is a placebo. Now, the placebo varied between the different studies. So for one of the studies, it was like a sugar pill, which did not consume caffeine, obviously. I think another one, they just didn't even take anything. And the third one, I think they took like fiber. It was like fiber within this pill. The participants did not know what they were being fed at the time. However, I know at least for one of the studies, the participants were then asked, well, what do you think that you were on after they took the pills and after they did the whole testing criteria? And most of them were able to figure out that they were on caffeine or when they were on the placebo, which I suppose isn't too much of a shock because, well, if you're taking caffeine, you're probably going to feel the effects of, that excitement, that higher level of awareness, not being as sleepy, things like that. Okay, so to discuss the amounts real quick, again, so it's 3 or 6 milligrams per kilogram of body weight. So if I did the math here, so for an 80 kilogram body weight person, they would be consuming 240 milligrams if they were given the 3 milligrams per kilogram, or 480 milligrams, obviously just double that, if they're consuming 6 milligrams per kilogram. And we're going to find out if the 6 milligrams ends up having a greater benefit, if there is an overall benefit, than the 3 milligrams. Now, in terms of the testing style for the runs, pretty simple. They just had them consume each of these tablets, the proportional amount that they were supposed to be consuming. I believe it was either an hour or an hour and a half, so it varied between study and study, but at least an hour between taking it and then actually performing the exercise itself. So then they would have to run 5 kilometers at a maximal pace, so as fast as they possibly could, or 8 kilometers, which is the other study, at a maximal pace. And then, of course, the outcome, the result is, well, how quickly were you able to run this 5 or 8 kilometers? Okay, fair enough. I think they also had an acclimation test run, because the reason why you want that as a researcher, let me go ahead and go full screen real quick. The reason why you want an acclimation phase, which means, to define that, you don't want participants that are foreign to the environment, to running, to cycling, whatever it might be, to test them right away. So the first time that they do this experiment, that you test them right away, and then the next time you give them caffeine or whatever and then test them again. The reason why that's problematic, potentially problematic, not always, but potentially problematic, is that a person may not be familiar or comfortable with running or cycling, or especially with cycling, you don't really know the bike that well, so you're not that familiar with it. So the difference between the first experiment and the second experiment may not necessarily be due to the treatment, the actual caffeine being given, but because the participant may be getting more comfortable with the cycling. So that can lead to a confounding variable. So most of the studies, I think maybe all of the studies, ended up having a kind of acclimation where all the participants ended up doing the experiment, but they weren't measured, they weren't tested on that. And then it wasn't till several days later, or sometimes weeks later, that they actually came in and did the actual experiment where it was actually tested for them. All right, so That is the study design. Take caffeine or take placebo, and then after an hour or an hour and a half, run 5 kilometers, run 8 kilometers, or if they were biking, they were set to a particular workload or they had to work a certain amount of that workload within a particular time. So they had to do as quickly as they possibly could. So if they had to output X amount of watts of energy, then they had to do that as quickly as they possibly could. So set amount of work in a particular amount of time. And of course, the shorter for both of these, the shorter amount of time that they did, obviously the faster and therefore the better performance. All right, so let's look at this first study. So honestly, most of these studies did not have graphs. So I just took the data. I took the data that they had in the studies, and I just created my own graphs. And these are, I used a statistical software to do this. So this isn't like me just like drawing an arbitrary line and just saying, yeah, this is it. No, this is all controlled within a statistical program. But ultimately, if you don't believe me, you can always just check out the study for yourself and look at the numbers as well. So this comes from study B. So that's why I wanted to mention A, B, and C, because I'm not going to be sticking to the order. It fits better in a story to start with study B. So study B, they looked at well-trained individuals, people that had 5 years experience running, or recreational runners. So people that just played sports but don't actually go out and run and whatnot, but just because they wanted to see if there was going to be a difference between the two. And they found that no, there was no difference. So there is an improvement from caffeine. So it's not a huge improvement. It's about a 1% or 1.2% improvement. And it was roughly the same for both. Now, statistically speaking, when you're looking at this kind of stuff, if you were to compare between these two, there's no difference. I believe these were confidence intervals. I don't have that in my notes, which I probably should have done. But if you're familiar with statistics, you know that this is a great sign that the actual improvement is at least probably around 1%, but it could be higher. It could be within like a 2% improvement, because the confidence interval just tells you with 95% confidence that the true value, the true change, is somewhere within this bracket. And I believe they did confidence intervals. If they didn't, then what I just told you is completely wrong. And we're just going to have to base it off of this black line, which is the average, the mean that they calculated. So 1% improvement roughly for kind of novice runners as well as more experienced, well-trained runners. Okay, great. Now let's look at study C, which not only shows us, so here we have our confidence interval, so 95% confidence interval is right here, this line, but ultimately here they're showing the 8 kilometer run. So the previous one was by process of elimination, the 5 kilometer run. And they're showing the time difference. So the amount of improvement or just change in general. So if it were a loss in time, it would be more on the negative scale. And if it's an improvement, so a reduction in time, then it's more on the positive scale. As you can see across all 8 participants, so this is the number or the overall change from the placebo versus the caffeine. And with caffeine, they saw this amount of seconds of improvement in their time, in their running time after running 8 kilometers. And so you can see that, like participant 1 had roughly about, let's say, 21 second improvement. Participant 3 had, let's say, like 7-8 second improvement. So, but overall, it was all an improvement. And then obviously, I'm sure you noticed that participant 2 had a huge boost, an over a minute improvement in their performance. But all of these numbers combined lead to this graph right here, which is the mean. So the mean was roughly like 23 seconds or something like that. And the confidence interval shows that no matter if this mean isn't exactly right, it's going to be somewhere within this confidence interval. It's going to be somewhere within, it could be as little as, let's say, like 15, maybe 14 seconds improvement to as high as, I don't know, 33 seconds. So that's how you typically read that. But in general, there was overall an improvement. But here, the point that I'm trying to get across here is that there's a lot of variability from person to person. Here, it's relatively equal. Here, you've got a person that sees an improvement, but not much. And then here, you've got this massive boost for this one individual. And the final piece of data to look at is to try to figure out, I suppose I should mention here, it was about a 1 point in the percentage scale. It was about a 1.2% improvement, much like the previous study. All right, so now looking at, is lower caffeine or higher caffeine better, or kind of better stated would be, if you consume more caffeine, do you get more of an improvement in your endurance? And here I should have added seconds, right? I think, yeah, it was seconds. On the y-axis, but I forgot to add that, so excuse me. You're supposed to have the correct titles for everything, but ultimately just know that it's seconds over here. So for cycling, this was a performance improvement in cycling. Again, the same result, that there was an improvement from caffeine. And again, I'm not sure if these are confidence intervals or if they're standard deviation for anybody that's interested in statistics. But ultimately, the low caffeine showed an improvement of, let's say, 160 seconds, something like that. And the high caffeine showed an improvement of, let's say, 125 or 120 seconds. So, you know, they did end up having a comparison between the two, and I don't think it was actually statistically significant in terms of the difference between the two. But they said that there's mild evidence or moderate evidence that higher caffeine intake is actually detrimental, slightly harmful. I think that's what they wrote. But ultimately, what we know for sure is that consuming more caffeine did not improve, did not add to the improvement that we saw from the lower caffeine intake. So this implies then that there is a threshold at which the performance no longer continues to improve. And some people did actually have a better performance on the higher caffeine, but most people did not see an improvement on the higher caffeine. And most people perform better with the lower dose, which is what we see displayed here. Now, there's a reason for that, and that is actually kind of what I'm going to be teasing in the next video that we're going to go into, where I'm going to show you a potential genetic anomaly that happens in certain individuals that could lead to caffeine actually being detrimental to performance, not only not improving, but actually detrimental. All right, so to start looking at these mechanisms, I realize this looks like a bit hectic, but don't worry, I'm going to walk you through it. I'm probably not going to walk you through the whole thing, but just walk you through parts of it. All right, so let's take caffeine out of the equation for a second. Ultimately, you may not be familiar with how muscles contract. So when you move, when you do anything, if you're running, if you're cycling, if you're moving my hands right now, you're breathing, any of that is controlled by these structures down here, which are known as sarcomeres. So you have a muscle cell, which is one cell of millions and millions of cells that make up your muscle. Let's say if you're running, let's do your quadricep. So you've got millions of these cells that are found within your quadricep. And within each one of these cells, you have all of these components. You have a lot more than just these components, but we're just going to be focused on these. So if we were to zoom into just one section of one cell, we would find that there's the cell membrane right here, which is what we see here as well. And underneath the cell membrane, so in the inner workings of the cell itself, known as the cytoplasm or the cytosol, we have this structure known as the sarcoplasmic reticulum. What you need to know about this is that it houses calcium. The reason why that's important is because the sarcoplasmic reticulum, when it's activated, and I'm giving you a simplified version, but when it's activated, it will release calcium, as we can see here by these green dots, will release calcium, which will then lead to this contraction of these sarcomeres. So these sarcomeres will come together. So just like you have a contraction when you're contracting your bicep, for example, or if you're pushing off with your quadricep, those filaments here, myofilaments, but here we're talking about sarcomeres specifically, which make up these myofilaments, the sarcomeres will come together and shorten the muscle. And then when they relax, they end up extending back out. So it goes from this more relaxed state to a contracted state. And the way that it's able to do that is through calcium. I'm going to leave that there. Usually I would go into more detail about exactly how calcium binds these, sarcomeres with troponin, tropomyosin, myosin, actin, all these different proteins that make up these filaments. If you're interested, you can check out I believe I released a muscle lecture, which was not received well by people because, I understand it's a very dry subject. So it got very, very few views, which is perfectly all right. But if you're interested in more detail on this, then you can check out, just type in like Physionic muscle lecture, something along those lines. It'll say I taught undergrads this muscle lecture because that's what I did. Okay, so ultimately you just know that sarcoplasmic reticulum, when it's activated, it releases calcium. Calcium then activates this contraction so that the muscles can then contract more, or can actually fulfill their function of contraction. Okay, so now let's reintroduce caffeine into this equation. So caffeine, what it can do, and this is a bit fuzzy in terms of the mechanism of exactly how, but the idea is that caffeine has a number of different mechanisms on muscle. One, it can bind what are known as adenosine receptors and it can increase the tolerance of pain, or it can reduce the perception of pain. So that's one aspect. I don't actually know now that I'm thinking about it. That may be more on neurons than muscle cells. But what it can do on muscle cells is that it can stimulate the activation of the sarcoplasmic reticulum. Again, there are some intricacies here that I'm glossing over. There's these receptors known as the ryanodine receptors, for example, and they ultimately lead to the activation of the sarcoplasmic reticulum. So with high caffeine consumption, or higher than just basal levels, you have greater release of calcium from this SR, the sarcoplasmic reticulum. The second thing that it can do is it may activate the L-type calcium channels, meaning that the calcium channels that are found on the cell membrane, so this is inside the cell, this is a depot of calcium inside the cell, the sarcoplasmic reticulum. Now, there are also channels that allow calcium from outside of the cell into the cell. So it's possible that caffeine not only further activates the SR, but it also may further activate, or actually activate, these L-type calcium channels. Another thing that it might do is it might lead to intracellular signaling. I briefly saw something about that it may promote the activation of a protein known as PKA, or protein kinase A, which will then also further activate these different calcium channels. Okay? And then finally, I wanted to add one more thing, is that caffeine can also lead to greater epinephrine release. So epinephrine can also bind the muscle cells and can lead to greater activation of this calcium release. So it's a bunch of different mechanisms all centered around how caffeine has an impact on calcium release. And again, this calcium release then leads to the promotion of more contraction of the muscle cells. So that was a lot to say, and it's not all displayed here. You're going to have to take my word for it, or you're going to have to go over to that muscle lecture to get a more detailed breakdown of this information. All right, mechanism number 2. Caffeine can also affect adipocytes or adipose tissue, so fat cells. And in doing so can actually lead to a process known as lipolysis, where it the fat cells, it releases more fat molecules. Now, in doing so, you have more fat molecules in the bloodstream, and those get sucked up by the muscle cells, which we've been talking about, and can also promote them undergoing what's known as beta oxidation, or can burn or utilize a lot more of these free-floating fat molecules. So caffeine activates the fat cells to release more fat molecules. These fat molecules are then sent or get taken up by muscle cells. Muscle cells then use them for energy through a process known as beta oxidation. So that's another benefit, especially if you're talking about maybe not so much for the short-term runs like 5 kilometers, but if you're talking about running like 50 kilometers, for example, this would be a benefit because then you're relying less on glucose and you're relying more on fat. Now, I'm not talking about it being a benefit in terms of fat loss. I'm talking about it in terms of if you are using more glucose, that means you're sucking up more glycogen from your muscle cells as well as your liver. And eventually, a professor of mine would always say that fat burns in the flame of glucose. And that's because if you end up running out of glucose, running out is a relative term, but end up depleting your glycogen levels specifically, then that can lead you to what's known as bonking when it comes to an endurance race, or you hit the wall. And that's because now you have to rely on this much slower energy supply almost exclusively, instead of having a nice mixture of glucose and fat. So it's good to have some glucose around and then focus on fats, as opposed to having no glucose around and only having fat. So that's kind of the point that caffeine, I'm making with caffeine, is that it skews things to be more fat oriented, sparing glucose while still using a little bit of glucose as necessary. That's a key word there, as necessary. And finally, the third mechanism that I talked about, and that was also discussed in these papers, and I did a little bit more reading in, is that caffeine. So here's the chemical structure of caffeine. You don't need to know this, but this is just the proxy for my own diagram for caffeine. So caffeine is here, and what happens is that it's metabolized into these 3 different compounds. You can see the percentages of each. So once caffeine reaches the liver, what happens is it gets attached by an enzyme, and that enzyme will then change the molecular structure of caffeine from this to, for example, paraxanthine. So here you get the loss of a methyl group, and then you get the production of paraxanthine, or you lose a methyl group here, and then you get theobromine. So that's kind of the point. The big one, however, is paraxanthine, in that most of it is metabolized into paraxanthine. Now, why is that important? The reason is that there's preliminary evidence, or some evidence out there, that shows that paraxanthine seems to increase nitric oxide production. If you're not familiar with what nitric oxide is, it's a molecule, it's a chemical that's released from your cells, and it has a number of different functions, but one of the functions that it has is called vasodilation, meaning that it will take your blood vessels, you have a normal tubular blood vessel, and it will actually allow it to, let me go full screen for this real quick. So let's say you're looking right down the middle of a hose. You're looking right down the middle of a blood vessel. Well, what happens is that when nitric oxide gets released into that hose, into that vessel, that blood vessel, we're talking like an artery, for example, then nitric oxide will bind to all the cells that make up that vessel and will allow it to expand. So now it's a much larger diameter, and you get more blood flow. So clearly, if you're running, or if you're cycling, or you're doing any endurance event, it's extremely beneficial to have more blood flow going through this, and this is from the side angle. So, we were looking as if we were looking into it. This is from the side angle. So you go from, normal state to having a larger amount of space to allow more blood flow through, and therefore you get more nutrient delivery, more oxygen delivery, get more CO2 removal. All those different metabolites are removed as a result. So, now, that all said, let me go ahead and talk to you about some conclusions here. So, in conclusion, consuming caffeine reliably improves endurance performance by 1 to as much as 6%. This is something that was talked about in one of the studies. Now, there's with significant variability between people, as we saw. More caffeine does not provide an added benefit, so 3 milligrams per kilogram of body weight shows an improvement, but more, like 6 milligrams or 5 milligrams, does not lead to greater improvements. And the mechanisms for these positive effects are thought to be multifaceted, so I just covered a few of them, but this is certainly not all-encompassing, just like pretty much always. But we have something like from greater calcium release, which causes a greater muscle contraction, to the metabolite of caffeine, so paraxanthine, having some known and unknown benefits, as well as a few other mechanisms, some that I've mentioned, some that I haven't mentioned, like lipolysis, for example. However, let me go ahead and throw this in here. However, certain people may experience worse performance from caffeine intake, and that's where I want to tease you into the next video. So if you're interested in a more detailed breakdown of how caffeine can be beneficial for some people and can then be less beneficial for some other people, and then can be actually detrimental to endurance performance for other people, check out the next video in this series. And with that, I hope that you learned something. Hopefully I answered the questions to your satisfaction, and I'll hope to speak with you in the near future.